In this video, you're going to learn about lattice energy. We're going to learn about it both conceptually and mathematically. So first of all, what is lattice energy? Lattice energy is the amount of energy you need to separate 1 mole of a solid compound, specifically ionic compound, into its ions. Now, the gaseous part we'll get into when we get into the actual calculations. So basically, it's a measure of how strong the ionic bond is. So it tells us how stable the ionic solid is. The lattice energy is based on Coulomb's law. Coulomb's law is shown on the slide. You can see that the energy is proportional to the charge divided by the radius. You can see that it includes the charge of the cation as well as the anion, and then divided by radius, where k is a proportionality constant. So what this tells us is that the lattice energy increases as the charge increases, and it increases as the radius decreases. So let's look at some examples of how the size affects the lattice energy. So notice what we're doing is there's 4 chlorides listed, so they all contain chlorine, and what we're doing is we're going down column 1 on the periodic table when you look at this table. So going from lithium to cesium, we're going down the column. So remember, we know the atomic size. We talked about the trends in the last chapter. The atomic size increases as you go to the lower left-hand corner of the periodic table. So as you're going down the column, the size is increasing. So what that tells us is the size is increasing as we are going down this list. Now once again, based on Coulomb's law, if you increase the radius, because it's in the denominator, that should decrease the lattice energy. And we can see that that's exactly what we see in this trend, that as the atoms get larger, the lattice energy gets smaller. You can also see it in the pictures over here. So once again, as you're going down the column, you can see that the cations are getting bigger while the anions are staying the same. And you can see that that decreases the lattice energy. So what's important here to note, when you're trying to compare lattice energy, always one of the ions will be the same, like in this case chlorine, so that you only have to look at the atomic size of one, or it'll be something where the size of both of them indicates the lattice energy increasing, so it'll be clear what the trend is. So we've saw how lattice energy is affected by the radius. Let's look at how the charge affects lattice energy. So once again, the larger the charge, the stronger the lattice energy. This makes sense. If you have a higher charge, there's going to be more attraction between the ions, and the ionic bond is going to be held, the ions are going to be held closer and tighter together, not closer together, but they're going to be held more strongly. So if we look at these 2 examples shown here, we have sodium combined with the fluoride ion and calcium combined with the oxide ion. You can see that the radius is approximately the same for this example. But what's different is the sodium and fluoride have a +1 and a -1 charge, and the calcium and oxygen have a +2 and a -2 charge. So the calcium plus oxygen, or the oxide ion, have more charge. So that means they're going to have a larger lattice energy, which I'm just going to write as E. Now, the charge will influence the lattice energy more than the radius will. And the reason for this is if you have a +2 charge versus a +1, you're doubling the charge. But the radius will not vary as significantly. So if you have to decide between charge and radius, always go with the charge. So let's look at a couple examples. So if we look at lithium fluoride versus lithium chloride. So once again, keeping in mind the trend for atomic size, remember the atomic size increases as you go to the lower left-hand corner of the periodic table. So since fluorine is above chlorine on the periodic table, so we have fluorine and chlorine, chlorine will be bigger, and that's what's shown here. The radius of chlorine is bigger. In this case, they are both a plus charge and a minus charge, so the charge is the same. So what's important is that the fluoride ion has the smaller radius, and thus the lattice energy is bigger. Now if we look at the next example, we have magnesium fluoride versus magnesium oxide. We can notice that magnesium is a +2 charge, the fluoride is a -1 charge, and the oxide is a -2 charge. So the charges are larger on the magnesium oxide. So remember, the charge is most important. So we would expect the magnesium oxide to have the largest lattice energy. But let's look at the radius as well. The fluoride ion has the smaller radius. So even though by radius it should be the ionic compound containing fluoride, we can see that clearly the charge is more important for the lattice energy. So once again, if you're trying to decide between the two of them, you go with charge. So this is another, just shows lattice energy of a bunch of compounds so that you can compare them. So it's helpful, let me get a smaller pen here, or a smaller line. So I'm going to draw a line under here. So you can see, once again, we're comparing, on these top three, we're comparing, oops, it disappeared on me. On these top three, we're comparing, lithium is the same, so what we want to focus on is the anion in this case. What we're doing is we're going down the halogen column. We can see that as we go down the halogen column, the size is going to get larger. As the size gets larger, the lattice energy is decreasing. So you can see that also with this next set of examples. Once again, the cation is the same, so we're focusing on the fact that we're going down the halogen column, and that means that the size is getting larger. As the size gets larger of the ion, the lattice energy is also getting, so not also, but the lattice energy is getting smaller. Now, another thing to point out is that all of the ones on the left-hand column are all +1, -1 ionic compounds. As soon as you start to get ions that are larger in charge, so for instance +2, -1, for these two, you can see the lattice energy is significantly changing. The lattice energy is at least doubling that compared to the ones in the first column because you have double the charge. Then you can see here we have +2 and -2. So once again, the lattice energy is increasing significantly. So you can see with this relationship that charge definitely has a huge impact. And of course, here you have a +3, -3 charge, so you can see it has the lattice energy of all. And the other thing to notice is that these lattice energies are positive. So if we go back to the definition of what lattice energy is, it's the amount of energy that you need to add in to break apart the ionic compound. So because you need to add energy, it's an endothermic reaction, and that's why it's always positive. I do want to point out that depending on the text that you're using, sometimes they show lattice energies as negative because it has a slightly different definition. So your teacher may have a slightly different definition of lattice energy. So you might see a question that's something like this. Put the following compounds in order of increasing lattice energy. So once again, we have Coulomb's law. Remember, Coulomb's law is that the lattice energy is proportional to the charge. Oops, let me undo that. The charge divided by the radius, where the charge is the most important. So first we need to figure out what the charges are. Sodium is a positive charge, sulfur is a -2, magnesium is a +2 and a -2. So notice they all have sulfur. So we have a +2 and a -2. So right away, based on charge, sodium sulfide cannot be the answer. So with magnesium sulfide versus calcium sulfide, they both have the same charge. Because remember, the higher the charge, the stronger the ionic bond. So next we want to look at radius. So since the sulfide is the same, we want to look at the magnesium versus the calcium. So once again, just a reminder that on the periodic table, the size gets larger as you go to the lower left-hand corner of the periodic table. Since calcium is lower than the magnesium on the periodic table, it will be larger. So larger calcium, larger ion will have a smaller lattice energy. So smaller E. So the magnesium sulfide, because it has the smallest ion and the most highly charged, it will be the largest. So it wanted us to put it in the order of increasing lattice energy. So the smallest will be the sodium sulfide. Then, because it has the +1 and the -2 charge, so it has the lowest charge. Then it will be calcium sulfide, because it has the larger radius. And then it will be magnesium sulfide. Okay, so that's what you need to do conceptually for lattice energy, is understand when ionic compounds have strong bonds, when they have weak bonds. The next thing that we're going to talk about is how to handle calculations. When you're determining lattice energy, we use something called the Born-Haber cycle. This allows us to relate lattice energies to things like ionization energy, electron affinities, and other atomic and molecular properties. It's based on Hess's law. So what you first want to do, and notice I've numbered these steps to kind of help you follow because the diagram is overwhelming at first when you first see it. But basically your first step and your overall reaction in Hess's law is that we want to calculate, let me get my pen on, we want to calculate the heat of formation of whatever compound we're trying to determine the lattice energy of. So this is going to be the overall reaction in our Hess's law setup. So remember, when you're doing the heat of formation, you want to form 1 mole of the compound from its elements in their standard state. So that is why we have the 1/2 for the fluorine, is because we need to make sure that we have 1 mole on the product side. So after you've written that overall equation, and there will be a delta H, remember the heats of formation can be looked up on the heat of formation table. So the next step is you take your 2 elements and you want to break them down into gases and atoms. So if we look at lithium first, notice that lithium is already an atom because there's no subscript, it's only made of atoms, but it's a solid. So since it's a solid, we want to turn it into a gas. Turning a solid into a gas is called sublimation, so the heat involved with that process is called the heat of sublimation. If we focus on fluorine next, fluorine is F2. That means it's a molecule. So we need to break the molecule apart into atoms. So that's why the F2 gas is turned into F gas, and that's using the bond dissociation energy, also known as the bond enthalpy. That will also be on a table that is provided to you on the quiz or the exam. Now notice that we're multiplying the bond dissociation energy by 1/2, and that's because we're only breaking up 1/2 of a fluorine molecule. So it's only going to take 1/2 the amount of energy. After you've formed gases and atoms, your third step is you want to form ions. Oh, and I forgot to mention about fluorine. Notice fluorine is already a gas, so we didn't have to do anything to the state of fluorine. So when we form ions, remember 1 we're going to turn into a cation, and 1 we're going to turn into an anion. The lithium is the metal, so we're going to turn that into a cation, so it's going to lose an electron. Remember, the energy involved in losing an electron is called the ionization energy. Now for fluorine, we're going to turn it into an anion, so it's going to gain an electron. So the energy involved with gaining an electron is known as the electron affinity. You'll be given all of these values that we're talking about, except for one of them. So in this case, we're trying to solve for lattice energy, so we would be given everything but lattice energy. So our last step is we take our ions and we combine them together to form our original ionic compound that we were trying to calculate the lattice energy of. Now this step is forming the lattice energy, or in this step what we're doing is we're combining the ions together and forming the ionic compound. Remember, this is the opposite of the definition of lattice energy. So the definition of lattice energy was that we break the compound apart into its ions. So since it's the opposite of the definition, we have to take the negative sign of the delta H to calculate the lattice energy. So let's actually go through the problem and show how you write equations to solve a problem like this. So this is how the problem would be given to you. So we want to calculate the lattice energy for lithium fluoride if the heat of sublimation of lithium is 155.2 kilojoules per mole, the ionization energy of lithium is 520 kilojoules per mole, the electron affinity of fluorine is negative 328 kilojoules per mole, and the heat of formation of lithium fluoride is negative 594.1 kilojoules per mole. So remember, the first step is that we want to write the heat of formation of whatever compound we're trying to, ionic compound we're dealing with in the problem. So in this problem, we're dealing with lithium fluoride. Lithium fluoride is a solid. And remember, we want to form 1 mole of that solid from the elements in its standard state. So we have, and actually let me move that over a little bit so I have room for my delta H values. So I'm going to write it here. So lithium fluoride is made of lithium, which is a solid, and fluorine, which is diatomic, so it's F2, and a gas. Now once again, we want to form 1 mole of the ionic compound because that's the definition of heat of formation. So I'm going to put a half in front of the fluorine gas. So remember, our second step is that we are going to turn each of these into either gases, into gases and atoms. So for lithium, lithium is already an atom, however it's a solid. So we are going to turn it into a gas. So this is the heat of sublimation because it's lithium subliming. So we're basically using Hess's law here, so we're going to be adding up our equations. So our delta H's all are going to be in kilojoules per mole. If you label it up here, then you're not going to have to write the unit on every single one. So this is the heat of sublimation of lithium. Now, so lithium is already a gas and an atom. Now we're going to focus on fluorine. Fluorine is already a gas, however, it's a molecule. Now remember, we only have half of a fluorine molecule. So we're going to turn that into atoms. When we turn it into atoms, we're only going to turn it into fluorine gas. Now you're going to look at the table, which is 9.3 on this slide. You want to find fluorine. This number on the table is the amount of energy it takes to break apart 1 fluorine molecule into 2 atoms. But we have half of a fluorine molecule, so we want half of that value. So we're going to take 1/2 of 159 kilojoules per mole. So now that we have turned everything into atoms and into gases, our next step is we're forming ions. So the lithium is going to turn into the cation. So it's going to form lithium plus, and it's going to lose an electron when it turns into a cation. Now when you write this reaction, notice that the charges need to balance. So we have a plus, on the product side we have a plus and a negative charge, which balances out to a neutral charge. If the charges don't balance, that means you did something wrong. So this is the ionization energy, the energy to lose an electron. So that is 520 kilojoules per mole. Our next step is to have fluorine gain an electron to form the anion. So when it gains an electron, it becomes fluorine gas. Now if you've done it correctly, one of the elements will have an electron on the product side, one will have it on the reactant side. And also you need to follow your stoichiometry. So we had 1 mole of lithium produced in the first reaction, so notice I put 1 mole in the third reaction. If I had produced 2 moles of lithium in the first reaction, I would have needed 2 moles of lithium in the third reaction. So always make sure you use the same number because we're going to have to cancel them out. So going back to fluorine, this is the electron affinity, the amount of energy needed to gain an electron. So that value is negative 328 kilojoules per mole. Now our last step is to combine our ions together. And we are combining ions that are in the gaseous state to form the solid ionic compound. So this often confuses people because they're like, well, how can it go from a gas to a solid? But remember, by definition, and I told you we would come back to this, by definition, lattice energy is the amount of energy you need to break apart an ionic compound into its gaseous ions. So that's why the ions are gases, but the ionic compound is the solid. Okay, so remember, this is our lattice energy step, actually the reverse of the lattice energy. So I'm going to write negative lattice energy to remind us that it's actually the reverse of the step. Now, we're adding all of these up to get our heat of formation. I didn't write the heat of formation value of lithium fluoride, which is negative 594.1. So, if you did it correctly, everything should cancel except what's in your overall equation. So notice the lithium gas cancels, the fluorine gas cancels, the electrons cancel, the fluoride gas cancels, the lithium gas cancels. We're left with the lithium solid, the 1/2 fluorine gas, and oops, I wrote gas here, that should have been solid, and the lithium fluoride solid I crossed that out. Excuse me, hold on. And that one, so those are what's left and gives you your overall equation. Now the very last step is we're going to add up all of these values in the column, and remember they should add up to our final equation. So I'm going to do that at the top since I'm running out of room. So we have 155.2 plus 1/2 159 plus 520 minus 328 minus, I'm just going to put X for the lattice energy, equals negative 594.1. Now make sure you include units. So we can't forget about units. So I'm going to put everything in parentheses. Let's see if I can get back to, oops, all right. Won't let me get back to my previous drawings. But basically the only thing I needed to do was to write kilojoules per mole and solve for X. When you solve for X, you end up getting, let me look up the value, you end up getting 1019. And remember, it should be a positive number. Let me go through one more example. All right. So this one, let me see, it's not switching slides. All right. Okay, here we go. Here's our next example. So once again, where we want to start is calculating the heat of formation of our ionic solid. So this time we have calcium chloride solid, and we want to form 1 mole of that from its elements in their standard state. So we have calcium solid plus Cl2 gas. Once again, chlorine is diatomic, so that's why it's Cl2. Now, the heat of formation of calcium chloride is negative 795. Now, that is the overall equation that we're looking for. So once again, I'm going to make a table. You need to show how you're adding up the equations to get your delta H values. Once again, don't forget to include units. There's a lot to think about in these problems, but don't forget. All right, so after we've written our heat of formation equation, remember we want to convert each of our elements on the reactant side into gases, and atoms. So if we focus first on calcium, calcium is a solid. So we need to turn calcium, and I'm going to write it up here. I want to turn calcium into a gas. We're going from a solid to a gas, so that's heat of sublimation. So we look in the problem for where it gives us the value of the heat of sublimation, and that's actually what we're trying to calculate. So I'm going to write X because that's what we're looking for. Next, we want to break the chlorine molecule into atoms. Now, you won't find the average bond energy probably in the problem. Remember, you need to look at the table. So we want to find chlorine on the table. We can see that chlorine is 243. Now we have one molecule of chlorine, so that's the amount of energy that it requires to break one molecule of chlorine into two atoms. So that number is 243. So that's our second step, forming atoms and forming gases. Our third step is to turn our atoms into ions. Now, this one's a little bit different because our cation has a +2 charge. So whenever you have a +2 charge or a -2 charge, you need to add or remove the electrons one electron at a time. The reason why you have to do it that way is because the values that will be given to you are based on it being removed or added one electron at a time. So for instance, notice in the problem you're given the first ionization energy of calcium. That's the amount of energy to remove the first electron. The second ionization energy is the amount of energy required to move the second electron. So that's why you have to do it one step at a time. So I'm going to write down the first ionization energy. So calcium losing one electron. So it only goes to +1 because it's only lost one. Remember, the charges need to balance. This is the first ionization energy. Okay. Then calcium loses the second electron. So it's starting from calcium plus this time because we've already turned it into calcium plus, so it turns into calcium 2 plus and one electron. Notice I'm also drawing states on everything. Remember, the delta H value is affected by the state, so it's important that you write the states. So the second ionization energy is 1145. So we've formed the calcium into a cation. Now we need to turn the chlorine into an anion. Remember, you need to pay attention to the stoichiometry. There are two chlorines. So when chlorine gains electrons, we need to do it for two chlorine atoms. So we're going to add 2 electrons because each chlorine atom gains 1 electron. So because we are multiplying, so this is the electron affinity of chlorine, the amount of energy required to or needed to gain an electron, but because we have 2 chlorines, we have to multiply the electron affinity by 2. All right, so that was our third step, where we form the ions. Our next step is to combine the ions together. Remember, that is the opposite of lattice energy. So our ions are the calcium ion and the chloride ion. Remember, pay attention to the stoichiometry from the previous steps. So remember, when you combine the ions, the gases combine together to form the solid. So this is the inverse of lattice energy. So the lattice energy that you're given in the problem is 2,195. We need to do the negative of that because that is the reverse of that equation represents the lattice energy. All right, so that's all of our equations. So our last step is we need to add all of our values up, and they should equal the heat of formation value. So we're going to add up So bear with me while I write all this down. Now don't forget, we need to include units. So you're going to set all of that. Oh, okay. I lost that. Again, it keeps having trouble with the pen. But you set all of that equal to the heat of formation value and then solve for x. When you do that, your x ends up being, let me look at the answer. The x ends up being 122 kilojoules per mole. And that is how you use the Born-Haber cycle to calculate lattice energy or any of the other properties like heat of sublimation, first ionization energy, heat of formation, any of those. All right, bye for now.